Say hi, Jackson.
Hi, John!
There we go. We're going to first tackle T-phase question because it's a fascinating one. And the question is concerning the integral from 0 to 1 of x ln x dx. Now, the question is whether this is an improper integral or not, because T-phase notices that the limit as x goes to 0 of ln x is negative infinity. So she fears that perhaps this integral will automatically diverge. So one of the interesting questions is, do I have to worry about that or not? Well, let's take a look at the entire integrand first. Because if the entire integrand goes to infinity, then we have to treat this as an improper integral. And if the entire integrand does not go to infinity, but goes to some finite value, then we have a point or removable discontinuity, and we can ignore it. So let's consider the limit as x goes to 0 from the right of x ln x. And the form for that limit is 0 times infinity, which we recognize as an indeterminate form, but sadly not L'Hopital's eligible. So what do I do with those indeterminate forms that are not L'Hopital's eligible? Rewrite it. That's right. We're going to convert it. So I'm going to need to take this guy somehow and put it either into the form 0 over 0 or into the form infinity over infinity. Any suggestions? I clearly am going to have to introduce division here somehow. Yeah.
X over ln x to the negative 1.
Okay. Let's try it. See what happens. What's my form now?
0.
Aha! So that is L'Hopital's eligible. Go for it. And then, down the bottom here. Yeah, I think your insight to write it to the -1 power was probably superior to my way of thinking.
So that would be
This happens to students at least once in their lives. L'Hopital's rule is not the quotient rule.
So you're saying derivative of
Yeah.
So 1.
Right.
so that's 1 over negative 1 over x squared.
No, outside, inside.
Would it be negative 1 over x?
Negative 1 over
I
x
think
ln
it's
x.
derivative.
Outside, inside.
Negative 2.
I'm embarrassed.
Negative
Oh,
ln x
negative
two
1.
times 1 over x.
Oh, 1 to the negative 2.
Okay. Now, local high school teacher arrested for throwing pens. How do we do? Well, unfortunately, our fraction got more complicated and our form is still 0 over 0. So this suggests that while I have the right idea, maybe I need a little bit different execution. I need to halt in my tracks right here and go back to this. Go back to this point right here and try something different. What could I try other than x over 1 over ln x. Absolutely. Mutatis mutandis. And now my form is infinity over infinity, which is also becomes eligible. So what do I get for my limit?
Whatever x over x.
Aha! And that simplifies to, the limit as x goes to 0 of negative x, which is simply 0. So this was a good learning problem. First of all, we observed that everybody is tempted to treat L'Hopital's rule as the quotient rule, and it's not. I've done it before. If you are sitting out there, you will do it at least once in your life and head smack. Second thing is to observe that we can convert multiplication into division by the reciprocal, and we can choose which factor we work with. And we're going to choose whichever factor makes the problem come out best. And the third thing is outside, inside. Please. Now, what does this allow us to conclude? This allows us to conclude that our integrand looks like this. I think you can see that this is going to go out to infinity. It's going to have a 0 at x equals 1, and it is going to approach 0 with a point discontinuity at x equals 0. So that my graph must look something like this. And what we're doing here is computing the net signed area in this region right here. We can ignore the removable discontinuity. Why? Because all we have to do in partitioning the interval 0 to 1 is to create a partition of negligible width at x equals 0.
Yeah, because it's like it goes to us to the left.
Yeah, exactly. And we simply place that removable discontinuity within that partition and ignore it.
What area can you
The area hasn't come out to 0. This is simply the integral coming out to 0. The area is going to come out to negative something. Let's go ahead and do that. So this integral is going to be equal to, looks like parts is called for. What's my u, what's my dv? I look at the other one. U equals x. No, I like it. U equals ln x? Yes, I like it the way you said it. Sorry. That's what you said. Yep. I heard you wrong. And so then du is 1 over x dx, and v is x squared over 2. So this gives us uv from 0 to 1 less the integral from 0 to 1 of v du, which is x squared over 2 times 1 over x dx. And here's where the virtue of choosing u equals ln x comes into play. We get cancellation and an easy integral. This term, ln of 1 is 0, and x squared ln x you can think of as x times x ln x, which goes to 0. So this whole term right here cancels out, minus the integral from 0 to 1 of x over 2, and I'll let you check that that integral comes out to 1/4. So that the overall net signed area is negative 1/4. Does that help? It's a great problem. It's got a lot of nifty features about it. Okay. Tomorrow we're going to be talking about an algebraic technique called partial fraction decomposition. And the idea behind partial fraction decomposition is that we are going to undo the process that you learned back in grade school. Of combining or adding fractions by finding the least common denominator. And to get at that, what I want to do is to introduce the idea of integrating, or excuse me, of taking the fraction 1 over x squared minus 1, and I would like to express it as the sum of simpler fractions. And in particular, what I observe is that the factors of the denominator are x minus 1 and x plus 1. And so that tells me that if I choose the right a and b, then I could rewrite 1 over x minus 1 times x plus 1 as a over x minus 1 plus b over x plus 1. Take a moment and see if you can re-engineer, reverse engineer what a and b should be. Work on that for a minute. You can do it in your head, or see if you can do it on paper. Got some ideas? Got some ideas?
Yeah, I think a times x plus 1 plus b times x minus 1 equals 1.
Ah, interesting. Okay. Go from there. Yep. Got an insight as to the problem. Take a couple minutes to work with it. And then we'll come back and try to take your insights and turn them into a procedure. Okay, Delina, you had an insight. What was your insight?
It was a times b times x plus 1 plus b times x minus 1 equals 1.
Good. Where did that equation come from?
Come from when you, that's just how you calculate the two vector to get 1 over.
Okay, yes. In other words, if I were to do a common denominator here, I would multiply top and bottom by x plus 1, top and bottom by x minus 1. And now the numerators have to be equal in order for the fractions to be equal here. And there it is. Got it. What are A and B? Justin shaking his head. Anybody have any insights? Go ahead. Okay. Good.
And then using the relationship and x equals 1 minus a plus b over a plus.
Okay.
Are we solving for x?
But we're not solving for x. I'm just trying to find A and B. Huh. Interesting. Let me introduce you to two different ways of thinking about this that are complementary ways. One is the method of undetermined coefficients, or the equating of coefficients. And the second is the method of special values. Undetermined coefficients is a more formally correct method. It is also a little bit more algebraic in nature. And that is this. This equation over here is a linear equation. Blah, blah, blah times x plus a constant equals the constant 1. So if I rethink the left side as 0x plus 1, and I equate coefficients, then it must be the case that a plus b
Equals 0.
equals 0.
Or A minus B equals 1.
That's it. You see it.
So A equals B or A equals 1.
That's exactly it. We can immediately solve by elimination. 2a is equal to 1, so a is 1/2. And a plus b is 0, so b is minus 1/2. And what we've done now is define our a's and b's. Let's just check it really fast. If I multiply here, my x's cancel out. 1/2 plus 1/2 gives me 1. Life is good.
Yay.
Yes, actually, it is the only solution. It is the only solution for A and B that will work. Because my A's and B's have to conspire to make the X's go away and to make the constants be 1. Yes.
How do you know that A plus B equals 0 rather than that?
Because the left-hand side of this equation is 0x plus 1.
I suppose, like, from that to get x plus b equals 0, is it just a coincidence? Like, you just somehow you get.
Think about it in terms of polynomials. Suppose I give you a polynomial, ax squared plus bx plus c. And then I tell you that this polynomial is also equal for all x's to x plus 3. What are you going to tell me? You're going to tell me that a is 0, that b is 1, and that c is 3. Why? Because the coefficient of x squared must equal the coefficient of x squared. The coefficient of x must equal the coefficient of x, and the constant must equal the constant. So here, I have a polynomial, 0x plus 1, and the coefficients of that polynomial must be equal.
Oh, I.
You see it?
Yeah.
Better? Good. Good. Very good. So that's the method of undetermined coefficients. What we like about it is that mathematically it's very formal. Basically, we're thinking about each of the terms of the polynomial as being separate, independent components. And we equate the coefficients of the polynomial on the left side and the right side, and we get a system of equations that we can solve. Like this. Let me show you the way I like to do it, which is,
Oh, that's not the way that you would do it?
it's not the way I would do it. The spirit of the special value substitution is to recognize that this equation must be true for every value of x. Let me say that again, and let's go back and look at the top. in order for this decomposition to work, it has to be true that it is satisfied for every single value of x. Which means that I can choose special values of x that will zero out various terms. In particular, if I let x equal 1, look at what happens to my equation. 1 equals a times 2 plus nothing. Boom. Done. If I let x equal negative 1, then 1 equals a times 0 plus b times negative 2. Boom. Done. That is really efficient. Isn't that nice?
Can you explain one more time, like, why can that x equal 1 be 1?
Because this equation must be true for all x. So I'm going to be smart about the x's that I think is true for. And I can use as many x values as I need to generate this. Yeah. These equations. In particular, if I had let x equal 1 right here, then I would have ended up with the equation. Yeah. Trying to see how this relates to this guy. It doesn't really work out very well.
Oh, I have a question.
Yes.
So like in this transformation, the domain actually changed.
Oh, that's interesting, because you observed that I happened to plug in values that were excluded from the original fractions. Yeah, good eye. That's very good. The reason that I can do that is that this equation has to be true for all x, right? Technically, it has to be true for all x in the domain. However, because there are basically an infinite number of x values, I'm going to end up with, going back to our previous class, an overdetermined set of equations. And that, in other words, I could plug in x equals 2, 3, 4, 5, 6, 7, 8, 9, and I could get as many equations as I needed to. And those equations would then be equivalent to the results of plugging in x equals 1 and x equals 1. And so because they're equivalent, I feel justified in plugging them in, even though I recognize that they were not in the original domain of the problem. Good eye. Okay, so let's see how this works out with a slightly more complicated example. And we're going to apply it to integration. Okay? In other words, we need to write this as the sums of smaller fractions. Well, the first question is, what are those fractions going to be? So we're going to need to take and factor the bottom completely,
Got it.
Oh,
like so.
yes.
And now, having factored the bottom completely, we're going to rewrite
You see?
our fraction like so.
Wait. Let us try to.
Yeah, keep going.
GG.
这个可麻烦了，我告诉你，这有3项。
Someday I'm going to get Rosetta Stone and the answer will be back.
Like after 10 years,
That's okay.
like you had like enough like Chinese students
Right.
finally figure out those math terms in Chinese.
Right? Yeah. Be writing them on the side as I go.
It's harder to right in
Oh,
Chinese. That looks more Korean.
That's more Korean.
That's the people.
Notice that the magic phrase here is clear the fractions, right? There you are. When I multiply both sides by that denominator right there, I should get this. I should get this. I should get
Can you
Yeah,
wait
we
a
can
little
use
bit?
rule rates when I'm seeing.
Wait, I'm almost there.
No, you're not.
Yes, I am. Wait. I'm almost there. I got
You got it?
I don't know this one.
Well, to find out if it's right, what I recommend honestly is plugging them back into here and seeing whether or not it works
Yeah, you
out.
can check it.
Yeah. Elliot, what special values did you pick?
0, 2, and
And when you let x equal 0, what do you find out?
the second term and third term equals 0.
So a is equal to what value?
Or 1/4.
Course.
Negative.
Watch those signs, yeah? Guys, the substituting special values is simple enough that you can essentially write the work like this. If I let x equal 2 as you suggested, what do you find out?
You quantify it.
Then we got the B term.
Uh-huh. A is equal to?
Uh,
108.
And if x is equal to negative 2,
It's the same.
what do we find out?
So 1/4 is.
We get 1/8. That's exactly right. Now, here's the payoff. This is kind of fun. So it's a little bit rewarding in its own right. But now I want to show you how this works out. Suppose I had a really nasty integral, such as the integral of 1 over x cubed minus 4x. You look at this and you're like, huh, it's not inverse trig, it's not anything that I know. And I certainly can't do parts, and I certainly can't do substitution. But if I decompose this into a over x
It would be negative 1
plus b over x plus 2 plus c over x minus 2. Now, all of a sudden, I can walk through, term at a time, and integrate with ease. And I'm done. Boom. Isn't that nice? That's really, really cool. Okay, well, we have just a couple of algebraic details to pick through in order to get a complete system here, because it turns out that not all polynomials can be factored into linear factors of truths. So we have to deal with that possibility. Let's do that at this time.
X squared minus 3.
Well, that's okay. I can just write that as x minus root 3 times x plus root 3.
Oh.
So that's not so bad. But, are we ready?
Yes.
Okay. Let's consider decompose. Over x cubed plus x. Okay. Well, first of all,
X squared.
this is an irreducible quadratic, and it is a fact of algebra that all polynomials can be factored into factors that are either linear or irreducible quadratics. But the irreducible quadratics cannot be factored over the reals. In particular, if I were to try to factor this into two linear factors, I would get x plus I times x minus I. And we all do complex numbers in this class.
Oh, really? Never?
Well, actually, we will one day, maybe 2 days. But it's going to be just like a days of the school thing. We're sticking with the real plane. Okay? And so since this is an irreducible quadratic, I'm going to have to write my decomposed fraction as a over x, here's my first term. Watch carefully. Plus bx plus c over x squared plus 1. And the reason that this is necessary is that when I divide 1 by x cubed plus x, actually when I just divide it by x squared plus 1, it is entirely possible for me to get a remainder in that form. So, where do I go from here? Well, actually, where I go from here is pretty much what I did before.
So why can't you write it as a over x plus bx over x squared plus 1 and then plus c? Would that make
I
sense?
can. It doesn't make any difference.
Oh.
Yep. So now I can go through and clear the fractions, and that gives me the equation 1 equals a times x squared plus 1 plus bx plus c times x. Just like so. But now life gets a little more challenging if I go for the special values. Yes, ma'am?
So, do you use the x plus c whenever you have an irreducible quadratic?
Yes, exactly. The bx plus c is going to be the total possible remainder when you transfer it. Yep. Life gets challenging if I choose various special values. Obviously, x equals 0 is a good choice, right?
B equals -1?
Why?
Oh, I used the other method.
Ah, so she switched horses here, and she went ahead and simplified this. Catch. It's actually what I do also, even though I wasn't going to teach it like that. And when you do, what you get is a plus b x squared plus cx plus a. Everybody see that? And from this, since all of that is equal to 1, and we know that a is equal to 1, this lets us conclude
A
that,
plus B.
yes, a plus b is 0, so b is -1,
C is 0.
and c is 0 also. So it turns out that undetermined coefficients is actually the most efficient method of solution here. I could have also done this by picking just any two x values at random, like x equals 1 and x equals -1, and plugging in. And if I did, I would get a system of equations in B and C, but it's not as efficient as doing the undetermined coefficients. Yeah.
So here, actually, we can skip the part, the C, right? Can we?
Yes,
Yeah, because if we don't have C, then we just assume that that's a zero there.
yes, right, exactly. So now let's consider what would happen if we had to integrate 1 over x cubed plus x dx. We would do our partial fraction decomposition and write this as the integral of 1 over x plus the integral of bx plus c over x squared plus 1. And this gives us a natural log here. And this also gives us a natural log. Let u equal the denominator, x squared plus 1.
Okay.
Let u equal the denominator, x squared plus 1. So du is 2x dx. This is repairable. And that's it. So notice that if the situation had been reversed and b were 0 and c were negative 1, then I would have had the form negative 1 over x squared plus 1, which is an arctan form. So you're going to see a whole lot of arctans and a whole lot of logs with these. How we doing? Good. So in terms of wrinkles, we're going to call this the irreducible quadratic wrinkle that shows up sometimes. And the irreducible quadratics tend to deliver us arctans and logs. I want to consider now a second wrinkle, which is repeated linear factors. And for that, let's consider something like this.
We're using a new method, right?
What's that?
If we're using a new method.
Kind of. So, first of all, I do some factoring to find out what factors I have. And I observe that I have this factor, x minus 1, that is repeated. It's a repeated linear factor. And so the question is, how do I handle that? Because you notice that if I try to do this, then it's silly.
Why don't you do two?
Right, exactly, right. And it's pretty clear that this is not going to be complete enough to get me a factor of x minus 1 squared, right? There's no way that I can get an x minus 1 squared out of this stuff. So this approach is not going to work because I've got this repeated linear factor. So a second approach that I could possibly take is maybe what I can do with this repeated linear factor is just treat it as an irreducible quadratic. And I could do like a over x, group all this together so it's a little bit cleaner. So this is actually a pretty good way to go. But it's not as efficient as it could possibly be. Why not? Because I could take and divide one of my factors, x minus 1, into that thing, and I would get rid of the bx, but I would end up with a remainder. So that when I do it, it turns out that this is probably the most efficient way to go. To write this as a over x plus, watch how I handle this, b over x minus 1 plus c over x minus 1 squared. And doing it in this way reflects the fact that I'm going to get some kind of linear and some kind of constant right here. But I can split it up most conveniently for the purposes of integration especially in this way, by doing as much division as possible. So we're going to handle our repeated linear factors by writing out one term for each degree of the factor. Once for the linear, once for the quadratic, and if I need cubic, once for the cubic, etc. But now the analysis goes exactly like you think it does, which is that we're going to clear the fractions. By multiplying both sides by the common denominator of x cubed minus 2x squared plus 1. And now a couple of special values pop out immediately. What two values are useful here?
1.
If I let x equal 1, what do I discover? What else?
0.
And if I let x equal 0, what do I discover?
A minus b equals 1.
No,
Okay. 0.
a equals 1. But now I'm kind of out of special values, right?
Then plug it in.
Yeah, let's substitute. I agree with him. Let's go ahead and substitute here. But also, let's choose a clever value of x. How about x equals 2? If I let x equal 2, and I substitute the values that I already have here, then I end up with the equation 1 equals a times 2 minus 1 squared plus b times 2 times 2 minus 1 plus c, which I already knew was 1, times 2. And that's not so bad. That gives us an equation 2b equals, not 2. So b equals negative 1. And the integral, now when it's, if we integrate that form, notice that my focus here has been on integration, because that's where we're going to use this a whole lot. But partial fraction decomposition has a lot of different applications in different areas of math. It's going to be the same as the integral, therefore 1 over x plus a negative 1 over x minus 1, there's my b, plus 1 over x minus 1
Square.
quantity squared. The first one gives me a log, the second one gives me a log, the third term does not give me a log. It is x minus 1 to the minus 2 power, repair product power rule, and we get negative 1 over x minus 1. So just be careful about those repeated linear factors. They're not going to give you logs. Well, this has been good work. We did more than I thought we were going to do today, so that's great. Tomorrow, we're going to apply this to a very famous differential equation called the logistic differential equation. And we're going to get a solution to the question, basically, what happens when you turn a population loose in an environment with limited resources? Thanks. See you later.